In this lecture, we will discuss about second fundamental theorem. So we start the second fundamental theorem. The statement of this second fundamental theorem: let G be any group and H be any normal subgroup of G, normal subgroup of G, and K be a normal subgroup of G, normal subgroup of G containing H, So then G over K is isomorphic to G over H over K over H. So we shall prove this theorem. Now for proving this theorem, we know that H be any normal subgroup of G. So here we use this because since H be any normal subgroup of G, normal subgroup of G means X inverse belongs to H, where X belongs to G and H belongs to H. So when H be a normal subgroup of G, so then G over H is a quotient group. Similarly, we have already discussed about the quotient group. So G over K is also a quotient group because both H and K are normal subgroup. Also a quotient group. So again, we know that K over H. So K over H is a normal subgroup. Of G over H. So when K over H is a normal subgroup of G over H, so then we can say that G over H over K over H is a quotient group. So when G be a group, H and K be a normal subgroup of G, so then we have G over H over K over H is a quotient group. Now, so we defining a function. Now we define a function. We take a function phi. Phi we have defined G over H to G over K. So by setting, we take as function phi of Hx. H work as a identity. Here K also work as a identity. So H of X is equal to Kx. So we take as output as Kx. So for every Hx, this belongs to G over H. Here we write down as X belongs to G. So X belongs to G. Now, when we define the function, so we shall prove that this function is well defined or not. So for first thing, we shall prove that function phi is well defined. Function phi is well defined. So we take two element of G over H. So let Hx and Hy belongs to G over H. For all, we take as X, Y belongs to G. So now we take hx is equal to hy. So when hx equal to hy, so we see that when ha is equal to hb, which implies that ab inverse belongs to h by the definition of subgroup. So HB is a subgroup. That means when H is normal subgroup, there is also a subgroup of G. So Hx equal to Hy. So this implies that XY inverse belongs to K. So XY inverse belongs to K because K is also a normal subgroup of G. So we can write down this as so H which is subset of. So you can in the first step you can write down this as uh, basically we can write down this as xy belongs to h. So when xy belongs to h, so this can imply that xy belongs to k, also belongs to k. So that means k is also a normal subgroup of G. So the element xy inverse which belongs to h also belongs to k. So we can write down as k, h is subset of K. So all the element of H belongs to K. So this is our equation number 1. Similarly, when we consider Kx is equal to Ky. So Kx equal to Ky. So we can write down this as by using the inverse of definition. That means AB inverse, when AB inverse belongs to K, this implies that HA is equal to HB. So K means KA equal to KB. So you can write down that here is KA equal to KB. So we take as KA equal to KB. So this can be written KA equal to KB. So we take as a reverse definition here. So XY inverse belongs to K. So we can write down Kx equal to Ky. So when Kx equal to Ky, so this can be written as function of X by definition is equal to function of Hy. So function of Hx equal to function of Hy. So by definition, we have written this thing. So by definition. So here we can say that function phi is well defined. Function phi is well defined. Now, when function phi is well defined, so we move to the function phi is homomorphism. Second is phi is homomorphism. So function phi is homomorphism. For proving homomorphism, again we take as let hx and hy which belongs to g over h. So then function of phi of hx into hy. Hx into hy, this can be written as function of hxy. So hxy, so when h is normal, so we say that if h is a normal subgroup of G, so that means hx into hy can be written as hxy. So this function of hxy by definition, we have defined the function. So this can be written as k of xy because function is defined as phi of hx is equal to kx. So by definition, so here this is the definition. So by definition, we write down k of xy. This k of xy, because k is also a normal subgroup of G, can be written as kx into ky. So kx into ky, or k is a kernel, k is a kernel. So then we again use the reverse definition of the function. So this can be written phi of hx into phi of hy. So phi of hx into hy is equal to phi of hx into phi of hy. So hence we say that function is homomorphism. So the phi is homomorphism. So when phi is homomorphism, now we shall prove that phi is onto. So we shall prove that phi is onto. So third, phi is onto. So again, we take the element of set B and prove that which have preimage in set A. So we take as we have element kx which belongs to g over k, g over k. So which implies that x which belongs to g So imply that hx belongs to g over h. So hx, so such that, because function which is defined as phi of hx is equal to kx. So hence phi is onto function. So this having the preimage in g over h. So function is onto. Now fourth, we have proved that kernel. So kernel of phi is equal to k over h. So k over h. So we can assume that. So let hx belongs to kernel of phi. Hx belongs to kernel of phi. So this can be written as phi of hx, which is equal to kernel k. So that means phi of hx equal to k. So this implies that phi of hx equal to kx by definition, which is equal to k. So here we can write down that kx equal to k. So this means that x belongs to k, because we know that the definition of HH is equal to HH is equal to H. So the small h is also belongs to H. So by this definition, we use Kx equal to K. So x belongs to K. So when x belongs to K, so this can be written as Hx. Hx belongs to K over H. So Hx belongs to K over H. So we can say that kernel kernel of phi, which is a subset of k over h. So this is our equation number 1. Now we move to further, so that we again let hk belongs to k over h. So we can write down where k belongs to k. So this is small k which belongs to k. So now we take as phi of hk equal to kk. So phi of hk equal to kk. So this kk, because k belongs to k, so this kk is equal to k. So again we use this definition, hh is equal to h. So we can say that h belongs to h. So kk, so this can be written as equal to k. So this means that hk, this hk, so this hk belongs to kernel of phi, kernel of phi. So when hk belongs to kernel of phi, so it means that k over h is a subset of kernel of phi. So kernel phi. So this is our equation number 2. So kernel of phi is subset from 1 and 2. So from 1 and 2, we see that kernel phi, which is equal to k over h. So k over h. Now we see that since g over k is a homomorphic image, is a homomorphic image of the group g over h. So by first fundamental theorem, so here we use the first fundamental theorem. So directly we can write down g over h over k over h is isomorphic to g over k.